All right, hello, greetings. Let's take a look at problem 3. So problem 3, the system 2-butanol water at 1.013 bar exhibits partial miscibility. Data for the system are given in the table below. Answer the following questions, neglecting the variability of mutual solubility with temperature. Okay, so the first thing I'm going to do is I'm going to sketch a phase diagram for my system before I even look at my questions and try and tackle them. Okay, and so we have water and 1-butanol, so it's going to be a partially miscible system, and so I'm going to get phase separation. So there's going to be an LLL region and then VLE region on top. Okay, and so I guess as an aside, for water mixed with alcohols, so if I look at the homologous series of linear alcohols, so methanol, ethanol, 1-propanol, 1-butanol, 1-propanol is the first system for which water and that alcohol are no longer completely miscible. So water and 1-propanol are miscible, water and 1-butanol are partially miscible. Okay, so here we have 2-butanol. All right, so how I'm going to go about sketching my sample phase diagram is the first thing is, so when I have water and 2-butanol, or 2-butanol is component 1 in water. Okay, so 2-butanol is component 1, water is component 2. Okay, and peeking at the data given here, all right, this is pure component 1. All right, pure component 1 in theory has the lower pure component boiling point, right? So 2-butanol is the most volatile component, although the difference is rather small. So when I have partially miscible systems, all right, you should expect that they are going to form a minimum boiling azeotrope. All right, minimum boiling azeotrope forming from unfavorable cross interactions between 2-butanol and water, which leads to that partial miscibility. Okay, so we're going to first sketch a TXY phase diagram essentially, in which you have a minimum boiling azeotrope, and then what's unique about our minimum boiling azeotropic system, in which we have two partially miscible components, is there's going to be a flat region of that bubble line. Okay, that flat region of the bubble line, where it goes from flat to curved, that's going to correspond to my mutual solubilities. Okay, so to give you an idea of what I mean as I sketch this, okay, now remember, it doesn't matter how well you can sketch. We're just trying to make a sketch to help us walk through the problem. Okay, so pure component 1, so component 1's my most volatile component, so it's going to have the lower pure component saturation temperature. Okay, so here they're pretty close, but we can make them slightly different. So now what's going to be different is when I draw my bubble line. Okay, it's going to come down, then I'm going to draw a flat region. Okay, and then it's going to curve up. Okay, my dew line, since it's azeotropic, is going to pinch my bubble line at some intermediate composition, and then lobe out on the other side. Okay, where my bubble line goes from flat to curved, these are going to correspond to my mutual solubilities. Where my dew line touches my bubble line, this is going to correspond to my azeotrope. Okay, so significance of my azeotrope would be if I had a mixture at this azeotropic composition, you would transition directly from liquid to vapor. All right, you go from liquid to vapor at the same composition. Okay, what's tricky about an azeotrope is if I start with a liquid mixture to the left of my azeotrope, then I end up in this left lobe of my VLE region. Okay, and I can't get vapor composition past that of that azeotropic composition. If I start in the right lobe, what happens is now my vapor compositions are actually less than my liquid compositions. Remember, this is my dew line. Okay, here's my dew. Okay, here's my bubble. So I'm actually going to get vapors with compositions less than my liquid. Okay, so kind of the roles of the most volatile component and least volatile component flip. Now, where partially miscible systems are interesting is what I'm going to do is, so we said assume or neglect the variability of mutual solubility with temperature. So, well, this is my mutual solubility at my azeotropic temperature. Okay, since we can assume it doesn't change with temperature, I'm just going to draw vertical lines down which will correspond to my phase boundary in my liquid-liquid region. Okay, so now where this is really interesting is if I were to start with a mixture, say here, okay, and I were to heat it up, okay, so flash it like normal, I'd enter my left lobe, okay, and I'd have some liquid in equilibrium with the vapor, where that vapor composition is greater, just like we said over here. If I had some Z1 and heated it up, well, now the rules are going to flip, because now I have this vapor in equilibrium with that liquid. Okay, so what complicates things when they're partially miscible is now if you imagine that I have a mixture of this composition, okay, what happens is when I'm in the two-phase LLE region, so if I had a mixture of this composition, I'm actually going to get phase splitting. Okay, so I would have, this liquid in equilibrium with that liquid. Okay, so now, and actually I don't want to be quite at the azeotrope. Okay, but if I have, say, a liquid here, okay, and now I heat it up, okay, what happens is I enter this two-phase region. Okay, so this liquid region essentially disappears, and now I have this essentially liquid phase in equilibrium with this vapor. Okay, and so where this can come in handy, if you will, is you can play around with the composition of that liquid phase to affect your VLE once you enter the VLE region. Okay, so there's all sorts of games we can play in terms of marching around the phase diagram. Okay, but anyways, let's get back to the question at hand. Here's my sketch of my phase diagram. Oh, so A, make a TXY phase diagram and annotate single and two-phase regions. Okay, so it's going to be similar. So below my bubble line, okay, and we can make this. So below my bubble line, so down here I have liquid. Okay, so here's going to be liquid. Then where it differs is between these two crossbars. All right, this is still liquid. Okay, but this is going to be LLE, right? So I will have two liquid phases. I'll get two phase splitting, so I'll have two liquid phases in coexistence with each other. Inside my lobes is still two phase. Okay, two phase. Oh, so this is still two phase, and then vapor up here. Okay, so when I have partially miscible systems, okay, again, they're going to be characterized by that LLE region down here. And then looking at the VLE region, I expect them to have a minimum boiling azeotrope, because the reason I get LLE is due to the fact that those two components don't like each other, right? And those unfavorable cross interactions are going to lead to minimum boiling azeotrope. All right, so that's A. So if I were to, that's annotate. So if I were to plot it, remember for my bubble line, I read X. For my dew line, I read Y. So I'd have T versus X, and then this T versus Y, and then same thing over here, T versus X, T versus Y. And what you should notice is I said there'd be this flat region of your bubble line for your partially miscible systems, where that would give you the two mutual solubilities. So if I look at T bubs, okay, I see that the temperature is constant from here to here, right? So this would correspond to my flat region of my bubble line. And so if I were to label these mutual solubilities, okay, this would be 0.04, okay, is good reference point 1. Reference point 2 is this is 0.48. 0.48. Come on, stylus. So it's got like this button on it where if I accidentally click with my thumb, it turns into an eraser. So this is 0.48. And then azeotrope, where's the azeotrope? So the azeotrope is where my bubble line and dew line pinch. So I'm looking here for where they're the same. And it looks like, so here I go 87.54, 87.84. All right, so it's going to be somewhere between, somewhere in this region, right? Because I'm looking for dew lines decreasing, okay, goes through a minimum and then begins to increase, okay? So the minimum, okay, it's got to decrease a little more. It's going to be just past 0.4, right? So T dew decreasing, goes through a minimum, and then it's increasing. And so it's going to happen somewhere between 0.4 and 0.3. Okay, so just for the sake of setting up this problem, I'm going to label the azeotrope at, say, 0.4. Okay, just for simplicity. All right, now B. Okay, so B, you're given 1 mole of a mixture that contains 2 butanol and water at 1 atm and 75 degrees C. Okay, so 75 degrees C is below that flat region of my bubble line, which we just said was 87.54 degrees. Okay, so actually, all right, so we said this flat region, all right, this is 87.54 degrees C. Okay, so that's my azeotropic temperature. That's also the temperature where I have this flat region. Okay, so I'm at 75 degrees C, so I'm below it. The system consists of a single phase, but its composition is not known. You add water dropwise at 1 atm, 75 degrees C, until you notice that a tiny amount of a second liquid phase has appeared when you've added 0.46 moles of water. What's the composition of the solution you started with? All right, so the basic idea would be water is component 2. Okay, now when we sketch our phase diagram, we're thinking in terms of concentration of component 1. So if I'm adding water to my system, so if I have a system which contains water plus 1 butanol, right, and now that system, so it's a beaker, right, it contains some moles of butanol, some moles of water, and I'm adding water dropwise. Okay, is the composition is X1 or Z1, right, the composition of my mixture, Z1, so composition or mole fraction of butanol, is that increasing or decreasing? Well, it's going to be increasing, or not, it's going to be decreasing, right? Because the moles of butanol are constant and the same. I'm adding water, right? I'm diluting it. And so if I were to look at my phase diagram then, if I'm going from one phase to 2, okay, it must be that initially I have some mixture, say, over here, right? So if I'm to the right of this, vertical, then I have a single liquid phase. Then if I'm adding water dropwise, that's going to correspond to decreasing the value of Z1. Okay, so I'm going to decrease the value of Z1 until I hit this vertical. Once I hit that vertical, then in theory I hit the two-phase region, right? Liquid region. It's similar to bubble point calculations that we've encountered earlier, and that it's a theoretical limit, right? But once my Z is this composition, then in theory I'm going to have a system of, or a scenario of VLLE. Okay, so I know that I must be to the right of that vertical because I have a single phase. Then I'm adding water, which means I'm decreasing the concentration of Z1. I'm decreasing the value of Z1 until I hit that vertical, which is where I hit the two-phase region. Okay, so in terms of B, okay, I know that Z1 final, okay, is going to be equal to 0.48. Okay, so the question is, oh, and do we know how many moles we add, right? So in B, we have 1 mole of a mixture that contains 2 butanol and water at 1 atm. And so we're going to add 0.46 moles of water. Okay. So I would say initially we'll say and not the initial number of moles total that we have is 1. Okay, where Z1 not, all right, is a question mark. That's what we're trying to solve for. Okay, and then we add, okay, N2, call it, say, delta N2, okay, or even just delta N will be equal to 0.46 is what we add. 0.46. Okay, so the question is, what is essentially N1 or Z1 not? Okay, so let's see. So in theory then, Z1 final, okay, since my system's closed and the total number of moles of butanol will be the same, then how many moles of butanol should I have? Well, that should be Z1 naught times N naught. So this is the total number of original moles I have with this number of moles of butanol per total number of moles. Okay, and then how many moles do I have in my final system? Well, it should be N naught, right? Initially I had 1, and then I'm going to add this delta N2 to it. Okay, so if I solve then, let's see. So solving then, I should have Z1 final times N naught plus delta N2, right? And I'm sure you could think of some better terms, is equal to Z1 naught N naught. So the Z1 naught is equal to N naught divided by N naught plus delta N2. Okay, and that is times Z1 final. Okay, and so it should make sense. This term is going to be less than 1. Okay, since delta N2 is positive. So in fact, you could calculate this as 1 divided by 1.46, because that's 1 and that's 0.46. And Z1 final is going to be 0.48. Okay, so this is 0.48. Hold on, but now does that make sense? So this is 0.48. That's this. Oh, my algebra is terrible. So that's Z final times N naught plus delta N2. Okay, so Z1 naught is, oh, I'm sorry. My algebra is just terrible. So, because Z1 naught should be greater than Z1 final, okay, because I'm moving to the right. So Z1 naught is N plus delta N2 divided by N naught times Z1 final. Okay, so this is greater than 1, because this is 1 plus 0.46, 1.46 over 1, so that's 1.46 times Z1 final. Okay, and so Z1 naught is greater than Z1 final, as it should. Okay, sorry, algebra mistake on my part. Okay, and this is another case where without having sketched this phase diagram, that would have been, tough just to get started, right? So I can't emphasize enough the importance of just being able to sketch, a phase diagram, right? I did this without even, doing, a nice pretty picture like they're asking in part A. Okay. C, 20 moles of 2-butanol is mixed with 80 moles of water as the system is brought to boil until 75 moles is in the vapor phase. How many phases are present at this point, and what is their composition? So, what's important here is, knowing what side of the azeotrope I'm in. Because the question is, once I enter the two-phase region, which one of these lobes am I in? Okay, so am I in the left lobe or the right lobe? Okay, so that's important. And then 2, once I'm in the left lobe and right lobe for a given composition, knowing what T-bubs and T-dew are to know if I'm in between that temperature range. Okay, but what this question should really be asking for is, what lobe am I in? And so if I just look at C, if I have 20 moles of 2-butanol and 80 moles of water, okay, so that would tell me that Z1 is 0.2. Okay, Z1 is 0.2 because it's 20 divided by 20 plus 80, 0.2, right? I can handle that. So if my Z is 0.2, that tells me I'm to the left of the azeotrope, okay, but I'm to the right of this 0.04, so I'm in my liquid-liquid region, okay, so say I'm somewhere where this Z1 is. So below 87.54, right, I'm definitely in this two-phase VLLE region where I get phase splitting. Then as I heat it up, I'm going to enter this two-phase region over here, okay, where I'm going to have this liquid in equilibrium with that vapor. Okay, so that's what's key here, is knowing what lobe I'm in, okay, which side of the phase diagram I'm in, and then from there, it's essentially just a lever rule problem, because what we're given is we're given that V is 75, All right, so essentially V over F is 0.75. So 75% of my system is vaporized. And so what you're going to have to do is solve your equilibrium expression and mole balance simultaneously. All right, so I think this is C. So C, essentially we're going to have a flash run problem where I'm going to have some, I think it was Z1 was 0.2. Okay, F was equal to 100. Okay, 100 moles. Okay, then off the top, we're going to have some V, and we're told that V1 is 75. Okay, coming out the bottom, I'm going to have some X, and then L1. You know, in theory, we could just write down 25 moles, but in theory, that's our total mass balance. Right. So if I use my total mass balance, I could just write down the L is 25 moles. Okay, but I'm not going to do it because I'm going to write down two mass balances in addition to our phase equilibrium expressions. All right. So here's what I have here. Were you given S for anything else? How many phases are present at this point, and what is their composition? All right, so basically, I want to solve for y1 and x1, and then at the same time we can solve for temperature. So pressure is known and fixed. That's 1 atm. But temperature I don't know. I don't know y1 and I don't know x1. And so how we're and I don't know L1. Okay, so I have 4 unknowns. But basically I have 2 mass balances and 2 equilibrium expressions I can employ. All right, so I'm going to have 4 relationships which I can utilize. Okay, cool. So I'll have a total mass balance. So F is equal to V plus L. So I don't need to write that as V1. F is going to be equal to V plus L. Okay, so I can solve for L. And then I'll have a constraint equation. So Z1F is going to be equal to Y1V plus X1L. And then, in terms of, VLE relationships here, all right, I'll say I'll have 2 VLE relations. Okay, or 2 VLE constraint equations. And so how am I going to go and solve this? Okay, so since we don't really have analytic equations, it can, kind of be a pain in the neck. Okay, and how do I want to go about this? Well, one way could be that if I take, so just to say I solve for L. Okay, so L is known. Okay, so now I have my component mass balance. So Z1F is equal to Y1V plus X1L. Okay, so if I wanted to essentially drive the lever rule, but it doesn't really matter. Instead, let's just divide through by F. So I'm going to write Z1 is equal to Y1 V over F plus X1 times L over F. Okay, and then let's say solve for Y. Okay, so let me write this as Y1 times V over F is going to be equal to negative L over F X1 plus Z1. Okay, this is V over F. Okay, and so what I probably should have done is to solve it slightly differently. So let's just say Y1 then is equal to negative L over V X1 plus Z1 F over V. Okay, so how you could go about this then is guess a value of X. Okay, so I guess a value of X. Okay, so looking at this equation, okay, I know L over V, I know F over V. Okay, if I guess a value of X, okay, so remembering that I'm in this left region of my phase envelope. So if I guess a value of X, okay, so let's just say I guess this X, okay, can I solve for Y? Okay, and then once I solve for Y, okay, so via phase equilibrium relationship. Once I solve for y, can I check to see if that y-x pair satisfies my mass balance? Okay. If it does, I found my y. If not, I need to guess again. Right? So, you could kind of tackle this in an iterative type of process. But that's essentially it. So I can iterate until I solve find the x for which that xy pair satisfies my mass balance. Then it'll give me y and x, and then to find t. Once I know y and x, I can come up to the data as well, and solve for my temperature as well. Okay, but essentially, you can think of this as an iterative solution. What would be better is if we had analytic expressions for our data, like we had in problem 1, or 1 and 2, that we had in problem 2, that would facilitate solving this. Okay. And then D, a mixture that contains 82% 2-butanol by mole is flashed to 1 atm. If the desired mole fraction of 2-butanol at the exit of the flash separator is 90%, determine the temperature of the separator and the amount of 2-butanol that's recovered. Right, and so essentially it's a similar problem. The big thing here is Z1 is 0.82, so you're starting to the right of the azeotrope, and so you're going to be in that right region of the VLLE region when you enter it. And since we're starting with Z1 is 0.82, and I want a stream that's 90% pure in butanol, now that's going to be in the liquid region, because remember, the role of the vapor phase and liquid phase essentially reverse now when I'm to the right of the azeotrope. Okay, so I'll leave it at that in the interest of not boring you too much, but hopefully that gets you going.